Good afternoon. We present our final project for the EMOF course taught by Professor Miguel Fernando Montoya Vallejo. Our team consists of Daniel Garcia, José Velázquez, José Rentería, Andrés Castillo, and Alejandro López. The automaton you will see below represents a historical scene from the Battle of Bald Mountain. For the presentation, we will follow a structure based on the requirements, characterization of movements, mechanical analysis, manufacturing method, and finally the working prototype. As can be seen in the image and according to the axis, the coordinate axis on the left, our mechanism is divided into three distinct movements driven by a single main shaft. Mechanism A on the left corresponds to the tank, which uses a set of bevel gears to generate a rotation of the turret around the y-axis. On the right side, which is mechanism C, it corresponds to the soldier, where through a cam and follower system, we transform the rotational movement into vertical linear motion, making the soldier raise and lower his head as a sign of mourning. And finally, mechanism B, which is in the center, corresponds to the projectile. We use a 4-bar mechanism to simulate the parabolic trajectory of the bus's shot.
Next, we will delve deeper into the engineering behind each of these components. Cam and follower. For the movement of the soldier's head, we designed a disc cam with a translating follower, as you can see in the displacement diagram. The cycle was designed to have smooth movements. It starts with a rise of 5 millimeters over 40 degrees, maintains an upper dwell for 160 degrees, descends again over 40 degrees, and ends with a lower dwell. This creates a slow, deliberate movement that simulates the soldier's lament. Gear train. For the rotation of the tank's turret, we use bevel gears to transmit motion between perpendicular axes. The design parameters are a crown gear with 35 teeth and a pinion that was theoretically designed with 20 teeth but was modified to 8 effective teeth by cutting in order to limit the rotation range. We used a module of 1.75 millimeters. It's critical to mention the mounting distance, 20 millimeters for the crown gear and 30 millimeters for the pinion. These were calculated to ensure the exact crossing point and to prevent jamming. 4-bar projectile mechanism. To achieve the parabolic movement of the projectile, we implemented a 4-bar mechanism. The lengths of the links are crank 20 millimeters, coupler 50 millimeters, rocker 50 millimeters, and frame 40 millimeters. When validating Grashoff's law, the sum of the shortest and the longest 20 plus 50 equals 70 is less than or equal to 20.
To the rest, 50 plus 40 equals 90. 70 less than 90. This confirms that it complies with Grashoff. According to Barker's classification, we get a GCRR code, which means it acts like a rocker crank, ideal for the main shaft to rotate continuously while the projectile makes its repetitive arc.
Manufacturing methods. Cutting is used for the components of the box that contains the mechanisms, such as the side cover, the top base, and also the flat links of the 4-bar mechanism. The reasons for using this process were high dimensional precision. The cut ensures very small tolerances, speed and repeatability, the ability to manufacture multiple identical parts without variations, and ease of assembly. The parts are designed with perfect fits and slots, which simplifies the assembly of the box. 3D precision was dedicated to the mechanical components involved in the transmission of movement. The bevel gears, the shaft, the supports, and some internal parts of the tank. This process is justified by the good mechanical strength of this material, making it ideal for the gears that generate the turret's rotation and for the supports that keep the transmission system aligned. Another aspect is the ease of manufacturing complex geometries. 3D printing allows for the precise production of bevel gears, something that laser cutting cannot easily achieve. Finally, resin 3D printing was used exclusively for the automaton's aesthetic elements, the soldier, the tank, the projectile, and the shell. Thanks to its high resolution and detail, it allows for capturing expressions, clothing textures, and aerodynamic surfaces. Lastly, its surface finish allows the pieces to come out with a smooth surface, ideal for painting and decorative finishes, which enhances the visual quality of the Monte Calvo battle scene. Here you can see the final assembly. The main shaft is supported by the bearings in the side covers, ensuring stability and smooth rotation. This shaft transmits the movement from the 4-bar mechanism through a pair of bevel gears. The supports, one laser cut and the other 3D printed, keep the input shaft of this mechanism aligned. Prototype validation. First, on the left side, two bevel gears with teeth on half of their perimeter and offset by 180 degrees move a larger gear connected to the turret, which oscillates between two angular positions. Second, on the right side, a cam converts the rotation into a reciprocating motion, smoothly raising and lowering the soldier's head according to the displacement diagram. Third, in the center, the 4-bar mechanism driven by a shaft imitates the parabolic exit trajectory of the projectile and returns in a straight line. Finally, the entire system is integrated to narrate the Battle of Monte Calvo with just a single motion input.